Hello, this is Mr. Cook, and I'd like to welcome you to the bisectors of a triangle section, section 5.2. This is the second one in Unit 5. On the computer, Unit 8. Feel free to do the Unit 8 on the blackboard as extra credit for your test. As you go through this, it might help you better understand it. There's some other different examples, different things you can do that could help you out. Alright, so we're going to get started here. Our objective is to be able to use the properties of perpendicular and angle bisectors of a triangle in this section. So we're going to start with just a little review from the last section. And in the last section it said we were dealing with something that looked like this. And so we have which statement must be true about the following figure for point D to be on the bisector of angle B. So we're basically looking for what statement makes it true that angle B, that this point D ends up bisecting the angle D out there. So that's what we're trying to find. And so what statement over here makes it true? So we just kind of need to look through and we need to remember our properties. And I believe our property that said if this is an angle bisector, if BD is an angle bisector, then the two sides out here must be congruent to one another as they meet as a 90-degree angle to the angles. And so that's what we were looking for, that AD and CD are congruent to one another, and so that's what we were looking for. Okay, so moving along, when this is just some definitions that we need to know. You might want to pause it and get these definitions. When three or more lines, rays, segments intersect at the same point, it is called concurrent. So as a little drawing, if I was to draw three lines or more, so here's a line, here's another line, and another line that goes through that point, those three lines are considered concurrent to one another because they all meet at one point. And the point of intersection is called the point of concurrency. So the point of concurrency is this point right here, and just some terminology that we need to talk about so that you can understand what's going on. So looking down here, we have our first theorem, and the theorem says the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices. Sorry about my handwriting there. Equidistant. I'll try it again. Equidistant from the vertices. So we're saying this point is equidistant from the vertices. So PA would be congruent to PB and PC. And so when we have our point of concurrency from the perpendicular bisectors, so you'll notice that these lines that meet at this point that is concurrent, these lines are perpendicular and they cut the side in half. So there's another line that's perpendicular that cuts the line in half, cuts the side in half. So that's what a perpendicular bisector is, remember. It meets at a 90-degree angle and cuts the sides in half. So that point where all three of those perpendicular bisectors meet is the same distance to each one of these, and I guess I better use 4 because that's the only one that's different. Each one of these guys is all the same length. Okay, so something we need to know. Okay, moving along, so in this one, the perpendicular bisectors of triangle ABC, so this is an example. If you want to pause it and try it on your own, you can. It says the perpendicular bisectors of triangle ABC meet at point G and are shown in blue. Find the length of BG. Okay, so try it and figure out what it is. And here's my explanation. This point right here that I'm making really big and dark is the point of concurrency for our perpendicular bisectors. They're saying the blue lines are the perpendicular bisectors. So that means that these red lines are the lines going to the vertices from the point of concurrency. So all three of these red lines are going to be the same length. And this is by the previous theorem. So BG has a length of 9, and that's really what we're looking for. You just need to know the theorems, you need to practice them, you need to make sure you really understand what's going on with them. Okay, so then we got a whole bunch of other things that deal with perpendicular bisectors. And this is basically saying the point of concurrency of the three perpendicular bisectors of a triangle is called the circumcenter. So basically we're saying that this is the center, and where this point is, that is equidistant to each point, if you were to draw that radius, that's a radius of a circle, that touches each corner equally. And so this point P in all of these guys are the circumcenter of the triangle. And of the circle that is circumscribed around it. And circumscribed means the circle is outside the triangle. And so we're going to have these terms throughout this section and throughout other sections. We're going to be talking about inscribed, circumscribed, things like that. Inscribed would be inside, circumscribed is outside, and so that's really what we're trying to do. You'll notice, though, for this one, that what I want to point out is this last question down here. What is the point of... basically, no, that's not what I want to add. What I want to add is that you'll notice that for an acute triangle, the point of concurrency of these perpendicular bisectors is inside the triangle. You'll also notice that for a right triangle, that the point of concurrency, that is the circumcenter, is on the triangle. And this is the way it'll always be for these. And the perpendicular bisector of an obtuse triangle is outside the triangle. And so that's the way it's always going to be for those guys too. So don't be surprised when you're drawing your perpendicular bisectors that it ends up outside. And so that's really what we're talking about, and we'll be doing more of this. And so it says, what is the point of concurrency called a point P? That's going to be the circumcenter. That is going to be the circumcenter of this. So hopefully that didn't mess it up too bad. Okay. So moving along. Then when we talk about angle bisectors of a triangle. The angle bisector of a triangle is the bisector of the angle of the triangle. Well, that seems kind of silly, but you'll notice these red dotted lines are our angle bisectors. And when we draw an angle bisector, that point that is the point of concurrency in there, this point that I'm going to darken, is a point that makes a 90-degree angle to the side, and then you can draw a triangle, or a circle inside the triangle that is inscribed. Well, the cool thing about the incenter, which is this black point right here, that's the incenter, it is equidistant to the sides. All these lines, when you draw a 90-degree angle to the side, they are all the same length. So for perpendicular bisectors, the point that's inside will draw a circle around the outside and is equidistant to the corners, to the vertices. Well, this one, an angle bisector, is a point inside that will draw a triangle inside, and they are equidistant to the sides, not the corners. And so, is this a perpendicular bisector? No, it is not. This is not a perpendicular bisector. It is perpendicular to the side. You can see very easily that this is not a perpendicular bisector because it doesn't cut it in half equally. Bisector means two equal pieces. So, talking about angle bisectors, that's what I was just saying, the angle bisector of a triangle intersects at a point that is equidistant from the sides of the triangle. So, PD, this length right here, is equal to PE and PF on this shape, because that's what the incenter is all about. It draws the circle that is inside the triangle, and the radii of that circle are equidistant from the sides. And so they're saying, what is the point of concurrency at point P called in this one? This one is the incenter. All right, so if you need to copy these down, please pause it, and we're going to move along. So then, for example 2, N is the incenter of the triangle. Find ND. And it says, hint, use Pythagorean theorem. So we need to find this length right here, ND. Okay, well, if this is the incenter, these guys are angle bisectors. And if you pause it and you want to do it on your own, that's fine. These guys are angle bisectors, and that which cuts the angles in half. And so you'll notice I'm not marking all the angles the same. They're all different. You'll notice, though, what do we know about from this point of concurrency here to the sides? To the sides that are at the 90-degree angles. Well, hopefully you remember from just the last theorem that all these sides are equal. So that would mean that if I can find NF, I could find ND. So that's where the hint that we use Pythagorean theorem, because you'll notice that we have a right triangle here with F and A, and we can go ahead and solve it. So that would mean to solve this one, NF which is standing in for ND because ND and NF are the same length from our previous theorem, is one of the legs, 16 is another leg, and 20 is the hypotenuse, because that is the side opposite the right angle. The right angle is here, even though it's not drawn in, and so that's how I know how to set up this problem. So NF squared will equal 16 squared, which is 256, which adds to 256 to get 400. If I follow my steps of algebra and subtract 256 across the equal sign, then I will end up with NF squared will equal 144. And then if I take the square root of both sides, I end up with NF equaling 12, which is the length, which is the same. NF, ND, and NE are all the same length, so 12 is the length of ND, and that's what we're looking for. So then it says describe the error in the statement. So then I want you guys to kind of look at this and try to find the error. So please pause it before I move on.